Hello, everyone, and welcome. Today we have two speakers coming up, the first of which is going to be Mr. Rossing, who used to be a SVP of engineering here, if I remember right, until May 2005.
April 1st.
April 1st. The other speaker today will be Iair, who is an astronomer at the Las Cumbres laboratories. So if you can please join me in welcoming, I believe that Wayne is starting off the talk. So if you can please join me in welcoming Wayne.
1, 2, okay. Hi. We're up here and I thought I'd tell anyone at Google who was interested about what I've been up to for what is now 13 years, practically. This starts in 1983 when I was at Apple working on finishing up the Lisa. We were also working on Macintosh stuff then. And some things sort of came together one day. Personal computers were getting powerful. At least they had 32-bit address spaces then. Disks were getting bigger. The internet was happening. It didn't quite take off for another 7 years, but we were moving out of the ARPANET and DECnet into the modern world of the internet. And I realized that you could do astronomy around the world by building robotic telescopes and putting them in good places, ideally in the south and the north. So I still have the New York Times Atlas. And if you look at this thing carefully, you'll see there's a number of spots that are particularly worn out. One in Chile, Urumqi, China, which we won't be going to, and somewhere around Cape Town. And geography actually says there are only 3 interesting spots to put things in the south. You have a fairly wide source of choices in Australia, but of the other 2 places, you're pretty constrained. But this was an idea, and so I started to pursue it as a sort of a hobby. And then late in the 1990s, I managed to get a small, very small telescope. I think my wingspan, I could touch both sides of the dome. It was very small, 50-millimeter lens, doing a survey of the southern sky. And the reason I did that was, how do you design and build something that runs on its own for years on end and sends you data back? And we started with, I think, a 25 kilobit link. That quickly got upgraded to a 50 kilobit link. Really huge. So I started figuring out you need to compress data, all kinds of things. This is a very interesting project. And then things went on, and then I was retiring to Santa Barbara with the idea, after Sun, with the idea of, okay, I'll go build this network. I'll scope it at 6 24-inch telescopes and get it going and see what happens. Just as I was sort of starting to get that organized, I got this phone call that led to my coming here. And so I took over from Urs, who was the first VP of engineering. I think, as he likes to say, I'm the first professional one. And the rest was history. But an interesting thing, when I was in my interview cycle, which, by the way, was just as rigorous then as it is now probably, I was 13 weeks in an interview cycle. And I don't know, but it's rumored I was the 54th person to be interviewed for this job. I'm not sure that's true, but I think it's probably somewhat more true than not. But I got the job. But in the final interview, I did ask Larry, I said, I have this project in mind. And I want to know, I want to be able to do it. So I really actually want to have an exit strategy. Now, this is not your average interview question going to the people who are hiring you. And I explained what it was, and they said, oh, that's great. If you get engineering to 1,000, you're free to go with my blessings. And I'm sure he said it with every intent that that was going to be indentured slavery for me for the next 10 years or something like that. And so the day I took over, there were 80 people in my reporting structure. It was, I guess, what we would still call operations, engineering, including search, and the people who ran the IT system for finance. So it was sort of, if you knew something about computers, or you could spell computer, or you could do anything with a computer, I had this little gang of 80 people, and that was what I found when I got here. And needless to say, 5 years later, blown through the 1,000, and we had gone public. And I thought it was time for me to step aside. And by the way, I had at least 4 or 5 of the people who succeeded me in this room here. So that's thank you for coming. And you've obviously had your own growth strategy. And some of you even had your own exit strategies. So it's been a grand success. So this is something that LCO is about. We used to have a different logo. It used to use the Google colors. But we found out in talking to a lot of people in focus groups that LCOGT.net is confusing to people. It's a tongue twister. And because we had used the Google colors in our logo, people actually thought we were a subset of Google. We were just, and so when you try to raise money, they say, oh, you don't need money. Google's got all the money. So it became confused. So about 1.5 years ago, we rebranded ourselves with this new vision. However, the rest of the thing is not rebranded. Let me see. What do I push to go to the next slide? It's a Macintosh. I don't know how to do this. Okay. So the goal was basically, I decided that if I was going to build this network, it would be interesting to establish a small scientific institute in the fine-honed tradition of like Lowell Observatory in Flagstaff, which was founded by Percival Lowell, and they did a lot of stuff on Mars. There was this other thing called the Carnegie Observatories of Washington, founded by Andrew Carnegie, which basically funded Mount Wilson, Palomar, and the Magellan telescopes down in Chile. So there's only like 3 or 4 privately funded scientific institutes in astronomy in the whole world, and we are one of them. So it's sort of a unique thing to do. And here's sort of at the height when we were pushing out our first set of 1-meter telescopes. You can see a bunch of them. We hit about 80 people at the peak, and we're down to about 35 now. And let's see, what do we have here? Well, I'll skip some of that. We have a board of directors and all that other good stuff. And our unique global telescope is designed for time domain astronomy. So you might ask, what is time domain astronomy? Well, basically, things change in the sky, in the universe. They often change on timescales of 1 billion years. Stars oscillate on timescales of years to months to sometimes days. There are certain transient events that recur, different kinds of cataclysmic variables and stuff like that. So there's a lot of stuff that's changing, but measuring it is difficult. And in particular, at most observatories, what happens is you get a night, but you share that telescope with 50 of your closest friends, and you get 2 or 3 nights. And you take your data, and that's it. So if something is changing at the scale of odd and strange, but weeks or months, you get a very small sample every once in a while, unless you have set up some other way to watch this. And it seems to me, it always struck me as odd. Why wouldn't anyone do this? The reason is, I talked to a lot of astronomers and they said, well, if anybody has enough money to do this, they're going to take that money and build the biggest telescope they can, because that's going to result in the most scientific output and papers published and careers made. And that's an honest answer. And so I didn't have to make a scientific career, so I guess I made a different decision. So Time Domain is what we do. Let me see if I get around here. I'll skip some of the stuff and get the pictures. What we have is we have 3 1-meters, 2.4s in Chile. I'll just sort of go around. We have a 2-meter telescope on Maui. This happened in 2005. We got extremely lucky. Just as I started this project that started in Britain got in financial trouble, and we were able to basically acquire it. And so we got a 2-meter telescope on Haleakala, and if any of you are visiting Maui, send me an email and you can get a tour. It's really neat. Then you sort of trundle over here to Coonabarabran in Australia. We have another 2-meter, 2 1-meters, and some small 0.4s. We have a contract that's waiting on the Chinese government to say, here's the rest of the money, and then we will be installing 2 1-meters in Western Tibet. There's a place called Ali, and it is probably, in my judgment, as close to being on the moon as is possible. It's at 17,500 feet. They get about 2 centimeters of precipitation a year, and there's nothing that's living there. So it's the world's most inhospitable spot, but it's got great astronomy, and this whole area basically clouds up all summer long with the Indian monsoon. So you can't do any astronomy here. So this is the magic spot, because then you pop down here to South Africa, where we have another set of telescopes. Then we have a site in Tenerife. We have 2 small telescopes, and we're in discussions that we hope will lead to this filling out with more. And then we have a contract with Israel, is it a Weizmann? Or? Tel Aviv. Tel Aviv University. There's a WISE observatory here, a 1-meter telescope, and we're putting a spectrograph on that. So in addition to these telescopes, we can do optical imaging. We have at a number of them state-of-the-art spectrographs fed by 1 or 2 of these things. That's a National Science Foundation grant we got to build yet another unique network. So basically, this is now up and running. We're waiting on a few things. Yes?
How good is the infrastructure in China right now?
It's almost non-existent, except the Chinese National Optical Astronomical Observatory wants to build this site up with the hope of putting an 8-meter there someday. Not our 8-meter, but their 8-meter. But we're sort of part of their training wheel. So we go there and we start help driving that development. So they funded about half of it. I think there's just a money crunch on dollars that flowing out of China that they have to sort out. So that's our big telescope, and it has no scale, except to say, this gear is larger in diameter than I am tall. So you can see that's what a 2-meter telescope looks like in its clamshell. This is our 1-meter facility. Let's see, looking at this, there's something funny about this. Oh yeah, there's some telescopes in the foreground, but these 3 are our 3 1-meters. This is our small one. There's now 2 of those. That's a telescope from Korea, but that's our big telescope. These are our little ones. I won't bore you with the details, but there's some things about this that are very special. Everything is identical. The filters are the same. The detectors are the same. The software is the same. So you can actually get results and merge them from these telescopes easily. Yes, sir.
What is your angular resolution and your brightness resolution?
Let's see. We go down to typically an arc second. We can do better, but usually you don't get much better than that. It depends on the site. Brightness, reasonably long exposures. I think we can get down to 21 first magnitude. We built the whole thing around Somebody else discovered it. It's changing. We measure it potentially 6 times a day, and often for weeks at a time if the weather cooperates. And that's the science that we get to do that no one else in the world can do. So we do all kinds of programs. In fact, we have approximately 70 to 100 programs operating now. They're all scheduled in a batch every few minutes, 10 minutes, 15 minutes, something like that. And we only have a small group of scientists. We have 5 sort of staff scientists, if you will, and then we have, I think, about 6 postdocs and grad students, something in that those numbers. Typically 10, and we couldn't even begin to use the time. But our partners, our hosts in the observatories have to get time, and then it's all organized, and we've developed these scientific consortia. So right now, there's about 100 programs operating, which is quite a high amount of productivity. Recent important results are the kilonova, which you're about to hear about. This is a world-class scientific result, and it just happened. It was just announced in October. This event happened. It was the morning before the eclipse, the day before the eclipse, the morning of the day before the eclipse. Right, and or maybe 2 days before. So all of our astronomers were all up with Alan, actually, in Oregon or wherever, looking at the eclipse. And this all sort of happened, and it's an interesting testament, which you'll hear about. Okay, other things we've done, you may have heard of Tabby's star. This is a different one. This is a different one. This is a supernova. That normally supernova, when they go off, they go up, they stay up, and they fade. And after a couple, 6 months, they're gone. They're just burnt out embers. Well, Iair, one of his collaborators, found a really unique one. So this is what happens when you have the time and the ability to do this kind of science. So the future is, okay, I'm running quick. Rob Pike, I know many of you know him. Rob introduced me to Tony Tyson, who came from Bell Labs. They both came from Bell Labs back in, I think it was '83. And at that time, Tony was talking to us about how do you build enough computing to digest the data coming out of a 3 gigapixel camera at a rate of every few minutes you get a new image, and how do you analyze it, how do you get it stabilized, how do you archive it, how do you get it to the United States, how do you get it prepared so the whole astronomical community can use it. And in 2003, that was still a awesome computing problem. Now it's just, it's practically a rack. Except I'm sure their scale is such that they still have a big data center or two. And NCSA in Chicago is the destination for that data, and they're going to be doing a lot of work. So this thing's coming online in 4 years. It will survey the southern sky every point every 3 days, and some points more frequently than that. It'll produce about 1 million events a night that says, at this point, something happened. And it'll say, it moved, it changed color, it changed brightness. Something will have changed. So it will give 1 million triggers a night that something has changed. We figure there's a few hundred to a few thousand such triggers. Yes, sir.
How do you not get false positives from the atmosphere?
You generally integrate for 30 seconds or so that often helps. And you might, a lot of things, you take 3 pictures. I don't remember exactly what Ellis is, but typically you take 2 or 3 and you median them, or you look for an outlier and you toss it out and use the other things. But the idea for us is there will be hundreds of events a night that will be moving up too bright for this thing to measure. And that turns out that they move into the area where we can do the measurements. So there are 3 or 4 other surveys coming prior to this, and then this comes on board. And so from basically 2022 to 2032, LCO is going to camp out, and we're going to study all that stuff. And we expect to find out lots of new physics. So that's basically where we're at. We built this thing, took a lot of work, and now it's working. And as to how it's working, I'll introduce Dr. Iair Arcavi, who's one of our postdocs, is an Einstein Fellow, which is something that comes out of NASA. Basically, they pay a salary, we give them a desk, and guess what happened?
Thank you, Wayne. Let me see, is this working? Sounds like it's working. Okay. Thanks, Wayne. So it's really exciting to tell you about this discovery that has all of us in astronomy very excited. It is one of the biggest things that has happened in astronomy in the last decades. As Wayne said, Las Cumbres Observatory turned out to be the exact thing you needed for a discovery like this. So this all happened on August 17th. It, I think, will be remembered as an important day in science for many reasons. So it was the first time we detected gravitational wave from the merger of 2 neutron stars. It was the strongest and best localized and closest event where we detected gravitational waves from. And it was the first time we were able to detect gravitational waves and light from the same event at the same time. The light from that event is what we call the kilonova. So that was the first time we've seen one of those. And it was the first time we identified which galaxy gravitational waves were coming from. Okay, now that is just a part of what made that discovery so special. But let me start at the beginning and explain what all of this means. So it starts, of course, with Einstein, who 100 years ago came up with the theory of how gravity works, a very elegant theory, which, okay, so here's the 30 seconds of what general relativity is. So the idea is that space and time, let's focus on space, is like a fabric that can be made to bend and curve and shift. And what does that is mass. So if you put a piece of mass in empty space, it will curve space in the sense that the distance between 2 points is going to change. And it is that curvature that is what we perceive as gravity. It's not a force. It's not that the moon knows that the Earth is there and so it orbits it. It's that the moon is just moving in a straight line in curved space caused by the Earth. Okay, so this was the idea. Mass curves space, and that is what we perceive as gravity. It was a totally revolutionary idea. And the summary of that is mass tells space how to curve, and space tells mass how to move. But of course, it's not just a story, an idea that he had and moved on. This is all rooted in math. So there are equations that you can calculate exactly how much mass curves space and how that tells other mass how to move. There are a lot of different equations. Okay, just to tell you that you can calculate this stuff precisely, and all of the observations done match the theory very exactly. But one of the things that came out of the equations that Einstein realized a year later was that if you can get space to bend, you can get it to ripple in waves as well. And the way you would do that is you take 2 very massive objects. So gravity, despite what we might think is actually a very weak force in the universe, you need a very big mass. You need 2 of them to orbit each other, and as they do, they will cause space to ripple. And as they do that, they use energy and they get closer to each other and go faster and faster and stronger until they merge. So this is what we call gravitational waves. It is waves in space itself that move through space. So the question is, how do you detect this? Okay, it's a very tricky measurement to make, because if you just take a ruler and a gravitational wave passes through, your ruler is going to get distorted with space itself. So you can't make that measurement very easily. The way this is done is with something called a Michelson interferometer, in case anyone's ever heard. You fire laser beams perpendicular to each other. They hit mirrors at the end. They come back and they meet each other. And if a gravitational wave passes through your detector, it makes one arm shorter and one arm longer, and then they oscillate.
and that changes the way the laser beams meet at the ends. This is, the idea was designed in the 19th century, but it turns out to be a super useful device, and these are huge versions of that. So these are what we call the LIGO detectors. Each one of these is this L-shaped interferometer. There's one in Washington State, there's one in Louisiana. Each one of these arms is 4 kilometers long because the effect of gravitational waves, even from a very massive object, passing through the Earth are tiny. The relative change in length when a gravitational wave like this passes through the Earth is 10 to the minus 21. Okay? And so that's the number you have to multiply the length of your arm in your interferometer to get the actual change in length that you're going to feel. So even with 4 kilometers long, this is about 1/1000th the diameter of a nucleus of an atom. This is what they're trying to measure. Okay, so in doing that, these are actually the most precise instruments ever built. And they have two, so that A, they know that they've measured something real. If you see it in both of them, it's not some fluke. And two, having two of them tells you where it came from on the sky, which direction it came from, and that allows us to know where it's from. There was a question.
Well, yeah, so is this really like the Michelson-Morley experiment that's trying to detect ether?
Exactly. It's the exact same thing that was used for the Michelson-Morley experiment, which tried to detect the ether, didn't detect the ether, and that ended up being the basis for the special theory of relativity. And now that same principle is being used to test the general theory of relativity and detect gravitational waves. Yeah.
There was also a third instrument.
Yes. Yeah, we'll get to Virgo. But this is the LIGO, the U.S. instrument is one in Washington, one in Louisiana. And they detected their first gravitational waves only less than 3 years ago. So in 2015, you may have heard, this made big news. The first time ever that gravitational waves were detected, this was from the merger of two black holes. So a lot of the press was very happy that Einstein was vindicated and proven right, which is great, but we didn't really have a doubt that it wouldn't work. The real importance here is that this is a totally new way to study the universe, right? For 500 years, everything we know about the universe has come from light. You build telescopes, you point them somewhere, you get light from a distant object, you study that light, and everything we know has come from studying light. Suddenly, for the first time, we turn on this new mechanism. It's not waves of light that are coming towards, it's waves of gravity. And it opens up a totally new way of seeing the universe that we couldn't see before. So just in this first detection, the merger of two black holes, we could not have seen that any other way. We only see them through their effect on space-time. And in fact, it was already a surprise, because the black holes that merged were about 30 times the mass of the sun each, and we didn't know there were black holes that massive, let alone in pairs, let alone close enough to merge. And this is now, the people who detect gravitational waves are physicists. They detected the waves, they're happy, they're done. And now the astronomers are, where did two 30 solar mass black holes come from to merge together? We don't know. So it's now a new problem we have to solve. The problem, though, is that black holes only emit gravitational waves. We don't see any light coming from black holes. They're black, right? So the really powerful discovery is going to come when we can combine the light that we see from an event and the gravitational waves together, and then really understand the physical processes that are happening. And we can do that if, instead of black holes, we look at merger of the next densest massive object in the universe, which is our neutron stars. So neutron stars are super dense objects. They're about the mass of the sun packed into the size of a city. Here it is at the top of San Francisco for scale. And at these densities, matter is totally different than anything we know. So we know these objects exist. They are the leftover cores of very massive stars that explode at supernovae. They leave behind this very dense, crushed core that used to be their center, a few times about the mass of the sun, about the size of a city. And it is so dense that the atoms get squished together in a way that this thing is essentially mostly made out of neutrons packed together very closely. So you can also think of this as a city-sized atomic nucleus. Or a city-sized star. Either way, quite fascinating objects. And so when they merge together, they will also make gravitational waves. But this is different than black holes merging together because it's a much more messy process. Nothing can escape a black hole, but neutron stars, stuff can still escape. So this is a simulation of two neutron stars merging. You see it's very messy. There's stuff flying out everywhere. And this stuff is very hot. And in fact, it was predicted that this is the only place in the universe when this happens where the heaviest elements can be made. So the heaviest elements in the periodic table, including gold and uranium and platinum and all this stuff that we know exists in the universe, has to have been made somewhere, and the only place where the conditions were right, we think, was the theory at least, is in these mergers of neutron stars. And as these heavy elements are made, they emit light, and then that is the thing that we would be looking for in parallel to the gravitational waves. If we can get both of them together, we'll be able to really figure out if that's what's happening. Okay, so here's what we expect from the merger of two neutron stars. This is an illustration, obviously. So we have neutron stars merging here. They're making gravitational waves. That's, you know, that ripple there in the grid, which are moving out through the universe. And then there's this stuff that is very hot that is forging the heaviest elements. And that is what's producing light that we expect to see. We call that a kilonova. And then there's also this jet of very fast material that gets launched, and we don't know exactly why, but the very fast-moving material, substantial fractions of the speed of light, gets launched in this jet and emits the highest form of light, energy light that we know, called gamma rays. And we've seen, you know, it shines in gamma rays for 2 seconds and then shuts down. And we've seen these bursts of gamma rays many times in the past, but you only see it if the jet is pointed at you. And so when we've seen that, that was the only thing we saw. It's this gamma rays from the jet, and then everything else was too far away, so we couldn't see the gravitational waves or the other light. So we've had this theory for a while that these bursts of gamma rays that we see are coming from this system, but we didn't know that that was the case. Now, the main problem in trying to do this is that when you get gravitational waves, they don't really know exactly where they came from. They give you a location on the sky. So there's a map of the sky, and this is the localization that they can say the gravitational waves came from something that happened somewhere over here. Maybe. It's still like this is the 90%, you know, sure, it could be anywhere. This is the actual localization on the sky from the first detection of the 2 black holes. It was somewhere in there. So for us with telescopes, it's very hard to go and find this. This is a large piece of sky. The other thing was that the light from this kilonova was very uncertain. People were doing calculations. What should this look like? Should it be bright? Should it be faint? What, you know, wavelengths would it be? Where should we look? And the predictions were kind of all over the place. Some people said, you know, it would be bright, it would be faint. Most people thought, okay, it will be faint and it will be red. So here's a problem we need to solve. We need to find something that's faint, red, maybe even in the infrared. Maybe we won't even see it in the optical light at all. And it's somewhere in this large piece of sky. Okay, so if you're a reasonable astronomer, what you do is you say, okay, it's faint, so I'm going to need a big telescope, because the bigger the telescope, the fainter things you can see. I'm going to need to put an infrared camera on it, and I'm going to need to design the camera and the telescope in a way that it can see large chunks of sky at a time. So that it can, you know, take a few pictures on that huge region. 1 second. Take a few pictures of that huge region, cover the whole thing as quickly as possible, because the other thing about the kilonova is it'll be gone in a week. This light only lasts a week or a few days, and if you take too long to search, you'll miss it. Okay, so, and indeed, respectable astronomers did exactly that. There are huge collaborations of hundreds of people led by Harvard professors that took the, you know, control over the largest telescopes with the largest cameras. And, you know, they're ready to go next time there's a gravitational wave event to look for it with this strategy. What we had at Las Cumbres was we gathered up about 10 of us and said, you know, this could be pretty important. But what we have is pretty small telescopes that only look in visible light and only see a tiny fraction of the sky in each image. Okay. And so it was like 10 of us, right, deciding. And we all looked at each other and said, are we doing this? So obviously we're going to do it. Right, and we were lucky enough to be able to convince the time allocation committee, who are the people who decide who gets time on telescopes, that we should do it. So I was happy that, you know, even though it looked like it's not the best way to do this, they still gave us the time on the network. Yeah, there was a question over there.
Yeah, I mean, what's the quick explanation for how they, when the gravitational wave was detected, that it was supposed to be from a kilonova and not from, as before, just black hole mergers?
So the gravitational wave signal itself, which I'll show you, you can tell what the mass of the objects that are emerging is. And so we this is an open question in astronomy, is up to what mass do you have a neutron star, and beyond that it becomes a black hole. But we know more or less, and the masses for this event that happened last August were fit what we think neutron stars masses are. But I'll show something about that later. So what we do have, though, is something that no one else has, which is Wayne showed you, is complete global coverage. So two things. A, we have telescopes everywhere. So as soon as this happens, we can get on it. We'll have a telescope in the dark. If these other big collaborations have their one big telescope in Chile, they have to wait for the Earth to rotate so that they can see it from Chile. The other thing we have is that it's all fully robotic. It's all software. We can just write scripts that will get the alert and send it to a telescope. You don't have to go fly to our observatory, call someone up, ask for a favor, observe this for us. It's all done by software. But how do we get around this problem that the localization is typically, this is another map of the sky that was one of the localizations from the black hole mergers, and our field of view to scale, that's what we can get a shot of with our cameras, right? So it would take months to cover the entire region. By then, of course, the event would be long gone. So how do we do that? So here's where we have to get a little bit clever and realize that stuff in the universe is not just uniformly distributed in space, it's in galaxies. And we kind of know where most of the galaxies are. It turns out we don't know where the small galaxies are because they're faint, but we know pretty much where all of the big galaxies are out to the distance where gravitational waves can be detected. So, if neutron star mergers only happen in small galaxies, we're screwed. It's not going to work. We won't know where to find them. But if, if there's a galaxy that has more stuff in it that also have more neutron stars, then that's where you should look, then maybe we have a chance. And so what we did was develop this system where LIGO sent an alert through this machine-readable thing. You have a listener looking for it. Once it gets the alert, it asks, okay, where in the sky is it? Send me that localization. It takes a list of galaxies that we know where they are and decides based on our best guess of where this thing could be, which galaxies to look at first. And it then sends that to the telescopes. Okay, we don't need any person to be involved. This can happen in a second. Of course, we did the first time. We did want to make sure, that this was working properly. So we have this web page. This is the actual alert from August 17th. And, pick 30 galaxies for us. Turns out, if you observe 30 galaxies in the region like this, you cover about 50% of the stuff in that region. That's pretty good. If you want to cover 100%, again, you have to observe a bazillion small galaxies, and that'll take forever. But if you just observe the 30 most massive ones, you get 50% of the stuff. And then there's a list of galaxies that goes down. These are the top 5 that it selected for us. And all we have to do is click the big green button to send it to the telescopes. Again, we could do this automatically, which is our plan for next time, but we just wanted to make sure everything was working. Okay, so that was the plan. Yeah.
What's your galaxy catalog?
Okay, yeah, the galaxy catalog is a whole issue. There are various galaxy catalogs out there. We use one called GLADE, which is a conglomeration of different galaxy catalogs. And some of the galaxies, you don't know how massive they are, so how do you take that into account? It's this whole heterogeneous data set that you have to eventually prioritize and decide, I'm going to observe these and not those for these reasons. There's a lot of details in there. Okay, so what actually happened on August 17th? So 2 neutron stars merged and produced gravitational waves. And you'll notice in this animation, which is what actually happens, they get closer and closer together. The waves become higher and higher frequency and stronger. Okay, until they merge and then they're gone. So that's a signal that the gravitational wave detectors are looking for, this frequency going up and amplitude going up. Here's what it looks like, is the actual data from that day. So this is frequency versus time. So this is, this merger has been going on for billions of years, but we only catch the last few seconds. That's when it's strong enough for the gravitational waves to be detected. And so what you see as this thing goes on, there's the signal at low frequency, and as time goes on, it gets higher and higher frequency and stronger, and that's where they merge. And that's the kind of signals they're looking for. So that's the actual data from the detector in Washington State. Now, you want to know, is this real? Did we see it in Louisiana? So the answer is yes, it was there in Louisiana. You could see it, but there's also that, which is a glitch in the system. So these kind of glitches happen when you have such sensitive equipment. It's kind of like a popping noise you get on, a stereo system. It's less than a second long, okay? And it happened every few hours, but they were not worried about it, right? Because obviously, what's the chance that a glitch will happen exactly at the moment that two neutron stars merge and the gravitational waves arrive at your detector, right? So the answer to the question is 100%. The chance is 100% that that's exactly when it will happen. Okay, the problem with this, of course, is the automatic software did not know how to deal with this. So they said, okay, we have a very significant detection on one side, don't know what's going on the other side, so we can't give you a position. Right, we need the two sites to measure the time difference in order to get the direction on the sky. So we knew it was something amazing happened, and we didn't know where. Okay, so that was one thing that didn't go as planned. They, of course, can remove this, right? You can see the signal here, so you can extract it, but you need to work on it for a few hours to do that. It's not immediate. So in the meantime, NASA's Fermi satellite, which is a satellite, a telescope in space that looks for gamma rays, these very high energy light that we think comes from the jet of these things, but only if we're lucky enough to be looking from the right direction. So again, we never expected to be that lucky, and we thought, you know, the jet might go in some other random direction, and we would never see the gamma rays, but 2 seconds after that gravitational wave arrived, a burst of gamma rays was detected. So here's what it looks like, you know, in real time. So there's a gravitational wave building up. That's a signal for Fermi. It's all just noise. And then the merger happens, and 2 seconds later, there's a burst of gamma rays. Now, we see gamma rays all the time, not that often, you know, a few, maybe one a day or something. So, you know, the chance that these things are not related and it just happened to be 2 seconds later is very small. In fact, of course, they calculated what the chance is. It's 5/millionths%. Is the probability that that is not related to that because it happened 2 seconds later. So we had, okay, so again, it's just telling us, okay, something very important happened. This in itself is already the first time that we've seen light and gravitational waves from the same thing. And they sent out this alert. It's called CBETs. These are like our version of a bat signal. When something interesting happens, okay, so they say the onboard trigger on the Fermi happened at this time is approximately 2 seconds after the single LIGO detection reported in this previous bat signal that we sent you. Now, the good thing is LIGO, Fermi, the satellite, knows more or less where in the sky this came from. It can give you some position, but it's even worse than the gravitational wave position. So here's another map of the sky with the localization. You know, this probability map, it probably happened here, maybe here, maybe here. And so that's all we had, you know, to go on. We only had the one gravitational wave detector, so they didn't give us a position, but we were lucky to get the gamma rays and get a position from that. And so here's an accurate depiction of our reaction, because of course, the way Fermi reports its localizations is a totally different format than the way the gravitational wave people do, which is what we have prepared all our software for. So we had no idea how to ingest the localization from the Fermi satellite. We never thought that's what was going to happen. Okay, but we did that, and we started observing galaxies in this region. Okay, and then 5 hours later, the gravitational wave people said, okay, we found this noise in the glitch, that it's a known type of glitch, and we were able to remove it, and the updated sky map that uses data from all 3 gravitational wave observatories, Hanford, Livingston, and V, which is the Virgo observatory, is now available. So Virgo is a third of these interferometers in Italy, and it had just turned on for the first time ever 2 weeks before this happened. Okay. It's a little smaller than the LIGO observatory, so a little less sensitive, and it turned on just 2 weeks before, but now we had data from all 3 observatories, so the localization was much smaller than it used to be when you just have 2. So here it is on the sky. When you combine those 3 gravitational wave detectors, then you're somewhere over here. So finally we have, you know, we were expecting a location for gravitational waves where to search. And then our reaction was that because we were looking over here, right? The Fermi satellite told us it's most likely over here, right? It said it could be here. But obviously we started here. So as soon as we got this localization, which was about 5 hours later, we told our telescopes, stop everything you're doing and now observe that area. So luckily our telescopes are obedient for now. They do what we tell them. And so here's, you know, one of our telescopes, and there's the actual galaxies it's observing, started going down the list of this galaxy list we had. Here's a map of the sky. So that's the moon for scale. Just to get an idea of, you know, this is considered a small localization. It's about, if you hold a banana at the sky at arm's length, that's about the shape and size of this thing that we have to look for. Those are the galaxies. We observe them. Galaxy number 5 on our list is one called NGC 4993. This big fuzzy blob is the galaxy, and this little point over here is exactly what we were looking for, the kilonova. And we know that because it wasn't there before. So there's the image of the galaxy from archival data, and the image of the galaxy we took that night, and that new point of light is exactly what we were looking for. And it turns out there were, these other groups who were doing this as well. We're all looking at the same galaxy within 42 minutes of each other. So these are all 6 images taken from the different groups using different strategies. Some of them use different galaxy catalogs. Some of them have the big cameras that they don't care about the galaxies, and they just took pictures of the whole thing and found it. And so as soon as we had that, we started, sending these things out like crazy. I saw this. What did you see? What does yours look like? Does yours look like? And then the space satellites from NASA wanted to get in the action too. The Swift satellite, the Hubble Space Telescope, obviously wanted to observe this as well. So as soon as the word was out, there were about 70 observatories on every continent observing this one event. And every continent, someone pointed a telescope in Antarctica at this thing. Okay, so pretty much every professional observatory on the planet and every professional observatory off the planet was observing this. Okay, so what did we see? So first image we took, this is how bright it was, about 150 million times the brightness of the sun. Remember, it's very far away. And that's the first image we got from our observatory in Chile. Now, as it happens, this part of the sky was only observable for an hour, and then it set. So anyone who just had their huge, amazing telescope that is just in Chile have to now wait 24 hours till they can see what it's doing. Okay, but we don't have to do that because we have telescopes in Australia. So as soon as the Earth rotated enough, we could see in Australia and we saw it got brighter. And then we can observe it in South Africa. And by the time we got to Chile again, to all those people that are now finally able to get their other observation, it was much fainter. So we had never seen something this bright evolve this fast before. It went from blue to red in just a few days, and it faded by a factor of 10 in just a few days. We've never seen that happen before. And also something we could only see happen with this kind of distribution of telescopes. And if you imagine that you only have a telescope in Chile, you only get every third point here. So you totally missed that it got brighter before it got fainter. And that turns out to be super important for the physics we're trying to understand. That it got brighter on about the time scale of a day before getting fainter. There's this models that went out the window as soon as we figured that out. But if you don't have that point, you just, you'd only think it's getting fainter, and you would miss everything intricate that's happening in between because this thing is changing so fast. So one of the things we learned by analyzing the light is what kind of elements it made. So this is where we thought the heavy elements are made. Now we know. Many of the light elements are made in the Big Bang. The intermediate elements are made by exploding stars, supernovae, and we didn't know where, we thought we knew, but we didn't prove it, where the most heavy elements are made. And this plot shows you now, from analyzing the light of this event, how much of the heavy elements are made in the universe are made in merging neutron stars. And so we've kind of almost solved this problem for many of the elements. The press obviously likes gold. So yeah, now we know where the gold is made. It's made in merging neutron stars. So if you have a gold ring or a gold necklace or something, the atoms in that we now know were made when 2 neutron stars merged, billions of years ago. And someone's wedding ring in NGC 4993 is going to be made from the gold in this kilonova billions of years from now.
Is the percentage of yellow there the percentage of that element that is made from these kind of events?
Yes, that's what we think. Now, there's a lot of uncertainty here because we've only seen one. So there's an uncertainty in how much did that one make, and then how common is this, right? So we're still, we're still working it out, but it looks like it works out that most of the heavy elements in the universe can be explained by this process. Another neat thing you can do is find a totally new way to measure distances in the universe. So we know how strong a gravitational wave should have been from calculating Einstein's general theory of relativity. 2 neutron stars of these masses merged. It should have been this strong of a signal. We know how strong the signal was when it got to Earth, so we can measure a distance to where it is. And so there we are. This is a paper that combines, the light with the gravitational wave information to get what we call the Hubble constant, which is this number that quantifies how fast the universe is expanding. So we know the universe is expanding. We know it's starting to accelerate its expansion for reasons we have absolutely no understanding of. And there are 2 main methods now that quantify this, how fast is the universe expanding. It's quantified in this number called the Hubble constant, which is about 70. And our 2 best methods until now for determining this number give different results. Okay, so one of them says it's a little bit under 70, and a different method says so we're about 70, and now we can use this gravitational wave event to measure this number, and what you get is that it's somewhere in the middle with this uncertainty, okay? So it's one event. It is a totally different way of constraining this quantity in the universe, and it gives, a result that's consistent with what we've been doing until now using other methods. But as the more of these events we get, this is going to get narrower and narrower, and eventually it's going to tell us where exactly this number lies. So from this one event, we've learned, where heavy elements are made in the universe. We've been able to learn a lot of stuff we didn't know about what are the physics of material at those conditions, at those densities. Things we call the neutron star equation of state. Right? We have very low constraints on, we now have some knowledge of. The fact that these gamma ray bursts that we've been seeing for years are actually coming from the merger of these stars has been finally proven. And, all the way up to the expansion rate of the universe. So I don't really know of any single event in astronomy that has ever taught us so much from the smallest scales to the largest scales. And there's still a lot of open questions, which is the even better part. So someone asked about the masses. So here are, this is masses in times the mass of the sun. So neutron stars are about 1 to 2 times the mass of the sun. The ones that merged in this event, we know were a little less than 1 point something, 1.3, 1.6, I think. And they merged to make something here. And one of the questions is, what did they make? Did they make a neutron star that's just more massive, or did they make a black hole? So here, black holes are this mass. Here are the ones that LIGO has seen, so very massive stuff merging. And there's this gap that we're trying to understand between the most massive, you can make a neutron star, and the least massive, you can make a black hole. And this thing that was made in this event, this happens to be either the most massive neutron star or the least massive black hole. Either way, it's pretty interesting. There are a few other events, a few other questions. For example, I thought this thing was supposed to be red. We were never supposed to be able to find it, right? It was totally lost cause for us, but it wasn't. The universe was very kind to Las Cumbres Observatory and made it bright and blue. So we could see it, but why? What is different? What was wrong with the models that predicted it would be red and it's actually blue? That gamma ray burst we saw was actually 100 times fainter than all the previous gamma ray bursts we've seen. So that's also an open question about what's going on there. And this thing happened 150 million light years away. It's nearby for our standards, but it happened 150 million years ago. That's the time the gravitational waves and the light were traveling to here, which, by the way, is another thing we have proven in this event. The gravitational waves move at the speed of light, which, of course, Einstein predicted and is totally true, but we've never actually measured it before. Now we know because they're all together. But if this would have happened 2 weeks earlier, so this was happened 150 million years ago, 150 million years the light was traveling to us. This would have happened 2 weeks earlier. We would have not have seen it because Virgo was off. So the position on the sky would have been huge, and we probably would not have found it. If it would have happened 1 week later, we wouldn't have seen it either because all the instruments were off a week later. That was the last week of their observing run. They were scheduled to shut down August 25th, and they did. Because the way they work is now they work a few months, they shut down, then they do improvements to be more sensitive and come back on again next year. So they were scheduled to shut down a week later. So if this would have, 150 million years minus 2 weeks plus 1 week, we would not have seen it. So again, either we were very lucky, or these things are much more common than we thought. And that affects, does that really, you start to get the opposite problem, they make too much gold and stuff than what we see in the universe. And then, of course, what did this make? So we learned a lot, and there's a lot of open questions. And I just want to mention, we did this with a team of 10 people in Santa Barbara, 7 people in Santa Barbara, and 10 more collaborators around the world that kind of gave us advice and helped us make this go and work. And, it's one of the things I love most about astronomy is you don't need to be in one of these huge collaborations and one of these, hundreds of people trying to do something. You can come up with an idea and just, do it with a small group of people and get it to work. Of course, assuming you have access to a very new and unique facility in astronomy that no one else has, because it's the only one of its kind that is there. So just a quick comment about what's next. So the detectors are off, as I said, they're improving their sensitivity, and they're going to turn on again in the fall of this year. So, we had this event, we're all scrambling like crazy, now they're off, we're all thankful for that. And next year, we don't know exactly, again, how lucky we were or how common this is. If it turns out we aren't lucky, it's just very common, this could happen as often as once a week. We could have one of these every week. So obviously we need to figure out how we're going to deal with that, but also just the amount of stuff we can learn from it is staggering. Other countries are building more detectors, so Japan and India. This is the one in Japan, which is going to be underground. It's going to turn on in a few years, and so the localizations are going to get even better, so we'll be able to find them even quicker. And they're going to be doing this from space because these things are so sensitive, these instruments. At some point, just the Earth is not quiet enough to do these measurements. The ground is shaking at some frequency all the time. You need to go to space to detect the lower frequencies of the gravitational waves. This mission was approved recently by the European Space Agency and NASA. They're going to launch these spacecraft. They're going to be flying millions of miles away from each other in formation, shooting laser beams, and sensitive to gravitational waves at much lower frequencies. So totally different kinds of things that produce gravitational waves in the universe are going to be discovered by them, not to mention the same neutron stars that maybe 5 years before were spinning a little slower. It's going to tell us, 5 years from now, on that day, at that second, there's going to be a neutron star merger at that part of the sky. So, start training a PhD student now to study that event 5 years from now. Yeah.
Is the detection ability linear? Is that going to be 6 orders of magnitude more sensitive?
It is. So it depends on what frequency. The idea of going to space is that we're not going to be detecting the same things that LIGO is detecting. You're going to be detecting gravitational waves at a lower frequency. So it's like you have a radio station that's just tuned to a different channel. So you'll see totally different things, but also the same things at different times. And this is the technology to do this doesn't exist yet. Okay, this is still planned, but they did have tests that worked much better than predicted. So this is really not just the one discovery. It's really just the beginning of a totally new way that we have to see the universe and learn how it works and learn what's going on. Thank you. So we can, I guess, do questions for both. We had some during, but happy to take more. Yeah.
So when you say you understand something, you have a new model. Einstein's models were equations. Are all your models simulations? You still have equations?
That's a great question. So the question is, are all models equations or simulations? Yeah. So we actually have two types of model. We call them analytical model, which are equations we can calculate, and numerical models, where we just put all the physics into a computer and let it run and see what happens. And there's benefit to both. The universe is mathematical to as far as we can tell, but it's mathematical in equations that we don't know how to solve. So at some point, we need the equations to get some intuitive understanding of what's going on, but then we need the simulations to actually solve it and figure out, what's actually going to happen. Even Einstein's equations, which are relatively simple to write down, took decades. This is another thing that made LIGO possible. It took decades to calculate what they mean through numerical simulations. There's a whole field in astronomy and physics that does this to actually be able to calculate what these equations say. And the fact that we know what a gravitational wave signature should look like is thanks to those calculations. So that's how they knew what to look for in the data. Yeah.
So how certain are you about that around 50 number? Is this what we should expect next year that would be varieties or?
Yeah. Okay. The full answer to that, it's between 1 and 50. Is what they expect next year. It's also kind of hard, to ask for the time location committee, give us between this amount of time or 50 times as much of that on the telescope, because we don't know, A, how common these things are. From just seeing one event, we can do a calculation. If we saw one in this time window, they should be roughly this frequent in the universe, but there's an order of magnitude uncertainty to that. And then we don't know how sensitive they're going to be able to make the instruments in the next run. So they're working on them, but it's an incredible feat of engineering, these instruments. It's not even clear what the sensitivity level is going to be. So when you factor those two things together, they say, yeah, we'll find between 1 and 50 the next year we turn on, and figure out how to deal with that.
There's an interesting thing. I keep saying the interesting thing about this thing is if there are no events, we don't have to put any telescope time on it. And if there's an event, this becomes the most important science we could possibly be doing. And the ultimate goal of these surveys is to figure out how we classify what comes out of them and then make the decision, is it important to do something right now? And it's interesting, even in LCO, there's a, shall we say, a degree of institutional resistance to the idea of just letting this stuff just run and making the decision. But the nice thing is you can do that. It's all software, it's all robotic, and hopefully none of the software has to ask permission.
Yeah, and this, yeah, I mean, in classical telescope, I would have to say, you know, here's the amount of time I want, and here's when I want it, right? I want it on September 14th, 2018, because that's when I think a gravitational wave event is going to happen, which is, of course, impossible to know. But LCO, we can say, okay, set some time aside in case this happens, but in the meantime, do whatever other 100 observations that people are asking for, thousands of observations. And when this happens, you know, that's when I'll let you know, from now to 3 seconds from now, you need to observe this thing. And I just send that to the software and it'll do it. I don't have to tell it in advance when this is going to happen.
How long does it take you to turn it on? From the time you say go, the time the telescope starts looking?
So from the time I tell the telescope what to observe until the shutter opens on my image can be between 5 and 10 seconds if there's a telescope that's in the right place and the sky is clear. So we can get on it in seconds. And that is the idea we plan for the next run, is to take the humans out of the loop completely. LIGO sends an alert, it figures out the galaxies on its own, sends a command to telescopes start observing. We can be sleeping when this happens. We wake up and it tells us, oh, I found this kilonova for you. You're welcome, go write the paper now. But yeah, seconds is the answer.
What took, I seem to remember that it took a long time for them to actually detect gravity waves. And if they're happening all the time, is that because their instruments, for a long time, they thought they were sensitive enough, but they weren't?
So this, yeah, the current way LIGO is running is called advanced LIGO. They ran before that for a few years in what they called initial LIGO, which was much lower sensitivity. And they actually knew, like from what we knew to expect of how often gravitational waves happen in the universe, they knew they would probably not detect anything. But they still ran in case, you know, the best thing is, of course, the stuff we don't expect. So they still ran for several years, also to test the, you know, this is all brand new technology. And they didn't find anything. They shut down. They did a huge upgrade. Essentially, it's a new instrument. And then, in fact, that first black hole detection happened during an engineering run before they had officially started to run. They said, we're in an engineering run. You know, there's this whole story about, you know, someone was supposed to be working on the instrument and was supposed to be offline, but they decided to go home early and left it online, and it caught that first black hole merger, which to this day was the best signal ever obtained. And that was on, you know, a week before they had planned to start the observing run. So as soon as they were at sensitivity, they started finding these. And there are now, I think, 5 black hole mergers that they've detected in the last 2.5 years, and this 1 neutron star merger. And when they come back next year, the rate's going to be even higher. So they were right below the sensitivity before, and now they're right where things are interesting. Yeah.
How did the physicists and the astronomers
Oh.
to work?
That's a great question about the physicists and the astronomers working together. So, you know, to many people, you know, say physicists or astrophysicists, it sounds like the same thing. These are actually 2 very different cultures. So the people who make LIGO are physicists. It's a 1,000-person collaboration. They're all working together for this one goal. They are super cautious. There are historical reasons why they're very, very afraid of saying they detected something when they didn't. And so as far as they're concerned, they want to detect the gravitational waves, work on it for like 6 months, and then when they're sure, they will let people know. Okay, now astronomers, very different. We still work in pretty small collaborations. We are very, you know, we want to get stuff out very quick. And, you know, we told them if you wait 6 months, there's no way we're going to find the signature because it'll be long gone. So the way we worked this out is we had to sign an agreement with them. And they signed an agreement, you know, it's just one huge LIGO collaboration, signed agreements with 100 different astronomy groups that they would let us know when they find a gravitational wave, you know, as soon as possible. even with the degree of certainty that they have at that time. And we can do our observations quickly, but then we have to wait for their okay to publish our data, right? They say only once we're sure, 2 months later, then we can all publish our data, right? The 10 hours after this happened, we were sure it was real because we had seen the kilonova, but they still needed to work on the data for 2 months. And so everyone worked on their data for 2 months. And then in October, 80 papers came out at the same day about this event. And that was only these groups that were in the agreement. Then all the ones that were outside then started analyzing the data. After.
Academic kilonova.
Yeah. It was, actually we have a webpage that we made of all the 80 papers, if you want to see them and sort them and look through them, because we all get lost in that. But it was really a clash of cultures. They do things very differently than we do. And there's one paper that we wrote together, which has 3,500 authors on it. 1,000 from LIGO, 1,000 from the people trying to detect neutrinos, which you didn't go into at all, and another about 1,500 astronomers across these 100 different groups writing this paper together. I was one of the people on the committee trying to get this to work, and I told some of the telecons it was really, to do a research on just
how long was the paper? 3,500 authors?
Well, including the author list or not? No, the paper is like a summary of everyone's observations, and it points to everyone's papers for different things. So I don't know, it's maybe 20 pages or something like that. But the author list is actually longer than the length limit for papers in that journal, just from the author list. And it was fun initially when they sent it out, they said, we think there are about 3,500 authors on this list, but we actually don't really know because some people might be in here twice, and like someone needs to just do a little research on the author list to figure out that it's okay. In particle physics, they do this all the time. In astronomy, this was totally new to us. So it was an interesting cultural experience for sure.
Why did they need months to double check when you had evidence hours later?
Yeah, this is how they work. Even the 2-month schedule. No, they believe. They send out this thing saying they give it a false alarm rate quantity on the alert that they send out, and this was a false alarm rate of one every 10,000 years, which means the chance that this is not, we get a signal like this that isn't real will happen once every 10,000 years, okay? And we saw the kilonova, it all worked out, but still they, had this is how they work. For them, this was a really quick turnaround. For us, it was excruciating. And I should say, another thing that came out of this discovery, which I think is not less important, is definitive proof that astronomers cannot keep a secret. Okay, we were sworn to secrecy by them through this agreement, but this is a tweet that came out August 18th. Like, we didn't even wait 24 hours. And someone, Craig Wheeler, who's a professor at the University of Austin, put out this tweet, which he later retracted. But, we're in astronomy, we're not built for these kinds of things at all. Like the Space Telescope, you can go on this website that tells you what the Space Telescope Hubble is looking at right now, okay? So when people trigger the Hubble, they have to put in a name for the target, and the person who triggered this put in, all caps, being binary neutron star merger, okay? And then this just automatically appeared on their website, okay? You think, okay, who looks at the Hubble website? Okay, we're fine, no one looks at it, except we had a Twitter bot that was tweeting everything the Space Telescope is looking at. So something appeared on Twitter like a few days after, I'm looking at the VNS merger, and here's a picture of what that looks like. And everyone who was not in on the secret was like, wait, what is going on here? And so this, rumors started flying, and, this is a great example. Anytime everyone says, NASA's hiding aliens, we are not capable of even hiding a neutron star merger. Okay? There's no way we could keep quiet about aliens. But, that was another part of the culture clash. The physicists were totally shocked that this happened. Yeah.
I was hoping that given you had a news embargo, you were able to go to see the solar eclipse, but it sounds like you were busy anyway.
I totally went to see the solar eclipse. It was the most amazing thing I've ever seen in my life because the telescopes are fully robotic. Once I told them what to observe, we were actually, once we found the kilonova, we had our telescopes observing that closely, but we also had other telescopes looking in other galaxies because we didn't know yet, is this a thing or is this going to turn out to be something else? And we'll miss it happening in some other galaxies. So we actually have this coordinated dance of like 9 telescopes, some of them looking at the kilonova, some of them looking at other galaxies, coordinating between them, and I was watching the eclipse because it's all done by software. Yeah.
Do you think the astronomy thing was just an organizational issue? They had 1,000 people with jobs, they're paid to do things, and it took them 2 months for them to say something?
No. I mean, they were working on, the thing is, they wanted to coordinate the publications. They want to, if they discover something and then some astronomy group weeks later is the first one to publish, they lose the credit for it. And I can understand that. They've been working for decades to make these instruments, right? We came up with this project 6 months before this happened, put it together, wrote the software, and discovered the kilonova. It doesn't make sense for me to publish it before them. So they're this big organization. They move slower. They want to make sure that they're the first ones to announce it, and then they allow us to do it. A nice thing that we did manage, I think, to convince them for next year is that the alerts are going to be completely public immediately. So no more of this secrecy stuff, which we've proven we cannot do. And also, since these things are brighter than we thought, actually amateurs with small telescopes can be the ones to find the next one. And that's great that it's public, because an amateur that has a small telescope might be at the exact right place at the exact right time to find it before any of us do. So we're really happy it's going to be public, and then, it's just going to be a battle to the death between the astronomers who publishes first. In one sense, it's allowed us to know no one else is going to publish this in the next 2 months, so we have time to all work on our papers for 2 months and then get them out synchronous the same day, But next one's going to happen. I know the Harvard team or the Caltech team are going to put out a paper in 3 days, so I better be quick if I want to be in there too.
Thank you very much.
Thank you.